Oh, thank you, everybody. And thanks, Sona, especially for the invitation. I realize you might be a little bit tired of hearing about broilers, so I'll try to switch it up and we'll talk about layers now. And I'll try my best not to eat up too much of your time into the lunch, but we have a few slides to go through. So I'm at University of Georgia, and my primary research focus is case-free layers. And then I've been looking at their skeletal problems and bones for a while now. So this is the status of current layer production in the United States. We have roughly about 330 million laying hens. And of that, about 35% is already in the case-free environment. So that means about 100 million birds. That includes organic and free range and everything that are in the case-free systems now. And this number is keep increasing every year. So if you go back and look at around 2015, we had almost 95% of them in the cases, and now we're closer to 35% of case-free production. So what that means is essentially this is a diagrammatic representation to just elaborate the changes, and you might have already guessed some of it. So going from case to case free means that the environment is more complex now. So the birds have perches, the birds have nest boxes, scratching area, and the birds can even come out of the system into a floor area, or sometimes referred to as a litter area. Other than that, in terms of the movement, in cages, the movement was, there was not any extensive movement of the birds. They were pretty much confined. But in the case-free environment now, depending on what the system is that you have, there is an opportunity for both horizontal and vertical ambulatory movements. The other big difference is the colony size of the birds. So in cases, 8 to 10 birds in a case, depending on the manufacturers. But now in the case-free systems, it can be from anywhere from 100, 150 to up to 500 to 2,000 and 3,000 in the same little area of the cages. So when we look at some of the welfare challenges in the case-free system, there was a comprehensive review that was conducted in the earlier times around 2010-11 when US was considering moving to case-free environment. So this was the time when Europe had just started moving to case-free houses at the start of 2012. So and then just to orient you to this table, so if you have more positive signs in the table, that means the problem was more severe in those systems. All right, so we've looked at feather pecking and cannibalism, which is seen more in case-free aviaries. Social aggression, again, it was more seen in furnished cages. Conventional cage and case-free were pretty much similar. Smothering and piling, it is a feature of cage-free houses, and you often see some of those panic smothering resulting in high mortalities there. Skeletal quality, you see conventional cage and aviaries almost similar with aviaries, slightly more severe problems, and I'll get back to it, what that means for the skeletal quality, because that's what pretty much we're going to talk about. And then there were footpad dermatitis and other welfare issues that are coming up, which are also more seen in the case-free aviaries. So when we talk about skeletal issues, one of the criticism that these conventional cages or the cage housing system faced was because of the lack of movement, and then the layers that are producing eggs, almost 1 egg a day for a longer cycle of longer than a year. What was considered was, so there was problems such as osteoporosis and cage layer fatigue. So those problems were not new. It started as soon as we started moving to the cages in the early 1950s. By the time we got into 2000s, some of those were ameliorated by breeding companies selecting against them. Improvement in diet and nutrition changed quite a bit. And then, but in cage houses, you could still see, you can still see signs of osteoporosis, especially in when the layer gets older or goes towards the end of production period. And then, so when you're producing or depositing a lot of calcium into the egg cell, and at the same time your movements are limited, that combination was the one that was considered predisposing these birds to osteoporosis or cage layer fatigue. And by the time of slaughter, you could see anywhere between 5 to 15% of fractures of humerus. Sometimes you would even see fractures of tibia, collapse of vertebral column. And then you can see some lame birds. And it was about 5 to 15% in those cases, the fractures, bone fracture at that stage. But what happened was, so now that we have moved to the case-free houses, we wanted to see by moving them, did we make any changes into their bone, or if their bones were getting stronger, or if the movement helped them in any way, right? So it takes a while to change the slides for some reason. All right. So we started this study in around 2012, 2013, when we were basically looking at what the housing changes means for the bones of the bird. And then, so, all right, so this is the conventional case systems. And on your right, you have a cross-sectional representation of a humerus, and then a cross-sectional representation of a tibia. So when you move, or when the housing system was changed, there were two groups of birds. Ones were raised until 18 weeks or during the pullet phase in the case-free aviary system, which is the system below. And then half the birds were kept in the conventional cases during the rearing phase. What you see in the change of the bone is you can see that the humerus responded to that case-free systems by increasing both, by adding layers of bone to their both periosteal area as well as on their endosteal surface. Whereas on the tibia, the changes were minimal, and you could only see some growth in the inner diameter or inner cross-section of the tibia. And if I translate this into saying like so then what that means, if the bones were stronger or not, means like if there is more bone deposited on the outer surface of your bone, that confers more bending resistance or more strength compared to the bones that are grown a little bit on the inside. The less changes in tibia also means that, because tibia is a load-bearing or a weight-bearing bone, right? Because the birds need, anytime a bird stands, it puts some forces on the tibia. So that means birds in the cages were also standing, or they could still stand and sit most of the time. So most of the changes in tibia are probably minimal. But you could see a really extensive changes in the humeri, and that tells us like the movement of the wing, the flapping of the wings or jumping up and down, that was the activity that was seen mostly in case-free, and you could see a more pronounced changes in those cross-sectional geometry of the humerus. And then when we looked at the mechanical properties, just to orient you to the graph, so the blue lines are the aviary birds, aviary pullets, and then the orange bars are the conventional caged pullets. So on the first graph, we have a moment of inertia, or the bending moment. So if to translate it into simpler terms, it just indicates resistant to bending, or when you try to break a bone, the process we do it called 3-point bending or uniform loading. So you put a bone like this and then put a force on top of it at the midpoint and then see where it breaks. So you can see both for tibia and humerus, the bending resistance was greater in aviary birds, which was kind of expected. And then when we look at the stiffness, or how dense your bone is, or how mineralized your bone is, you could also see that the aviary birds in the aviary, kept in the aviary system or reared in the aviary system, had stronger mechanical properties there, or they were more stiff. But just to put you a little caution there, sometimes, especially towards the end of layers, or when they're ending the production period, if the bone starts to become more and more mineralized towards that point, and then it starts to become really stiff, which acts like in a opposite way, because the more brittle a substance is, more easily it breaks, right? So if I drop a glass rod compared to a plastic rod, the glass rod will break easier. So stiffness is only good up to a certain point, but if the bone is too stiff, then it has a more chance of brittle fractures. So what we did next was, so what we tried to do was, okay, so by allowing them to move during the pullet phase or in the rearing phase, the birds, you see some positive changes in the bone cross-section, you see the changes in some of the bone biomechanical parameters, right? So what happens, because at that point, there were still some production environment or production scenarios where you were rearing birds in a floor system and then moving them into cages when they start laying eggs, or the other way around. So we decided to look at what happens, like if the bone mass that was gained by exercise or by movement during the pullet phase, would the bird sustain it during the lay phase, even though the environment was changed and they were put back into the cages? Or because that means then you can, because you only gain a lot of bone mass when you're younger. At a certain point, then you start getting it more mineralized, but you're not going to make your bones thicker, right? So we did an experiment where we had birds reared in aviary system, and then when they start laying, we either kept them in aviaries and then or moved them to the cages. And then we had birds that were reared in cages, and once they start laying the eggs, they were either kept in cages or they were moved to enriched colony cages. And what happened was, so this was the bird, like a micro CT scan of a cross section of a humerus. And then when you see that bird that was moved, that was reared in aviary, you saw that the bone was quite thick. It had gained quite a bit of bone mass. But once you start moving them into cages at the lay, the outer cross sectional diameter is still the same, but over the time, the birds lost significant amount of that bone mass that was gained during the pullet phase. So you could see that when you move them into cages, it lost some density, and because of that, it lost some stiffness. And then when you look at their mechanical properties, the Young's modulus or the material strength of the bone itself, that was decreased as well. And then we also had a group that was moved from cage to enriched colony cages. So enriched colony cages is, if you have to think about it, think about just a larger cage where the birds have opportunities to walk, maybe do a small jump, and then the flock size or the stocking density is around anywhere from about 40 birds to 90 birds is what they keep in the commercial systems. And even moving them from cage to that slightly more extensive environment in the lay phase, it would bring some positive changes in cortical diameters or cortical area, bending moment or the moment of inertia, stiffness, and some of those other material properties. And that was for the humerus. For for tibia, we didn't see any geometrical differences. So if you have to summarize all that study, can I give my copy? Thank you. So if you have to summarize, like you can gain bone mass by allowing birds to move during the pullet phase, but that positive change in bone mass will only be sustained if they are allowed to be kept in a similar environment during the lay phase. The other thing was providing movement opportunities even in enriched colony cages, which is only slightly more extensive than the conventional cages, could bring some positive effects. So to answer the question by moving them from cage to cage free, was the skeletal properties or the problems of the layers solved, right? So all the results that I just showed you tells us like it is, right? So you see some changes in geometry, you see some changes in structure, you see some changes in their composition. But what happened was we were starting to see a lot of these in the cage-free houses, or at least the reports in cage-free houses of fractures of the keel bone or the breastbone. So we ended up moving or trying to resolve 5 to 15% of fracture of humerus in cages. But then when the birds move to, or when they transition into aviary, then we start seeing like up to 80 to 90% of these keel fractures in a flock. And then these are different images of different types of fractures that I've seen over time. You can see the bones with multiple fractures. You can see a big fracture callus mass, severely deformed keel bones. So you could see all different kind of fractures in these birds. So I've seen up to 7 or 8 fractures in a single bone in a bird, and that the bird is still living and then producing an egg. So, but once we look at the data later, you'll also realize, or I'm going to explain, like this was not only the problem of cage-free houses. So only when the European Union started moving to cage-free houses, the birds were moved to these extensive systems, and then keel bone problems were started to be reported. But if I take you back even to the times of Darwin, like the first reports of keel fractures was reported by Charles Darwin in his book of natural selection. And then his theory back then was he saw deformed keels in chickens. And then he thought that was primarily because these chickens had lost their ability to fly. So because of that atrophy of the breast muscles, the keel bones also reacted in the same way. So the problem is not new. I would like to say that it has just resurfaced with the added attention of the cage-free houses nowadays. So I've focused on most of my work in this area or trying to look at keel bone. So let's go and look at it. So just to give you an idea, sorry. So in European Union, around 80% or greater than 80% fractures were reported in commercial aviaries, and around 66% were mid-keel fractures. In reports from Canada, 40% in floor houses, 25% in conventional cages. And in the US, we have seen 70% fractures at 56 weeks, and then around 30% at 26 weeks. And then we'll go on to it in a little bit more detail. So the first study we wanted to look at was if it was different for different housing systems and if it was different for different genetic lines of the bird. So in this study, we use two commercial strains, Highline Brown and Highline Silver Brown. And then we had a sort of a hobby or a backyard strain, Barred Plymouth Rock. So the Barred Plymouth Rock had about 15 to 20% less egg production to these contemporary birds. And then all these three lines were either housed in conventional cage-free litter and slat facility, or a single tier cage-free house, and in a free range paddock, cage-free house with access to free range. So when we look at the keel bone density, so this is the radiographic density based on the CT scans, we saw that, in this graph, CF refers to the cage-free, CC is conventional cages, and FR is free range, whereas HB is Highland Brown, SB is Silver Brown, and BR is Barred Rock. So you could see that the conventional cage birds had the lowest density of the keel bones, whereas the cage-free and free range had more denser keel. And then Barred Rock had more denser keel compared to the other two commercial strains. But when we look at the keel bone fractures itself, so the scores, the bones were scored on a score of 0, 1, 2, 3, and 4. And these are the images that are representative of that score. So score 0 means almost a perfect keel. There is no deviation, no fracture recorded. Then based on the number of fractures and the amount of deformation that bone had, it kept increasing up to score 3, whereas score 4 is also a severely fractured keel bone, as you can see, but that fracture looks completely fresh and unhealed. So most of those fractures were during the perimortem time when you are euthanizing the birds at the end of the production period. So we wanted to score it separately because the pathogenesis for those fractures might be completely different than the healed fractures and deformation. So on the top that you have distribution of keel severity score. Average keel fracture score was not different for any housing type, not for the cages, not for the cage-free. And then the average keel fracture score was not different for any genetic lines. Even the Barred Rocks, they all had a very high percentage of fractures. But if you look at the distribution of scores, you sort of see the conventional cage birds had more of a score 1 compared to the cage-free houses, whereas at the same time, they also had more of those fresh fractures or the score 4. So that means probably the birds were starting to get osteoporotic towards the end of production. And when we try to sample the birds, we are causing those fractures while trying to reflect the keel bone. Whereas when you look at the genetics, line differences, again, the same thing there. The Highland Brown and Silver Brown had more of a severity score 2 and 3 increased, whereas if you look at the score 1, the score 1 bird or the less severe keel fractures were more seen in those Barred Rocks compared to the other birds. So to summarize, range and cage-free birds had denser keel, but having an improved keel density did not really matter in terms of whether having a fracture or not. So for line differences, Plymouth Rock had a tibia that had a thicker and denser cortex, but all housing systems and genetic lines were associated with greater than 90% of keel deformity. So, and this is a more recent analysis or compilation of keel fracture or damage status across different housing systems. So this was compiled by Christina and Maya from UC Davis, and then this is on a review paper. It is a really nice review paper, and you can see that on an average, the conventional case had about 23%, 23.5% keel fractures, whereas the single tier aviary was the one that was reported to have highest number of keel fractures. The N number on the top refers to the number of publications on those houses. And then the assessment method, you can see a lot of studies in aviary particularly were done using palpation. So when you talk about palpation, you run your two fingers along the line of your keel bone and try to feel for fractures or deviations. And this was the primary mode of assessment that was employed in Europe. However, nowadays, if it's towards the end of flock, you have the luxury of euthanizing that bird and dissecting and looking at the keel directly. Sometimes our group has used CT scans and longitudinally scan the birds throughout the production period to look at the bone. So this is the overall status in different housing systems currently. So that was primarily about housing systems. So when we wanted to look at some of the genetic lines in more detail. So in this next study, we used 2 brown lines and 2 white lines from 2 different genetic breeding companies. And then the birds were housed during the rearing phase in a floor and a slat facility like the one that is depicted on the top. And once they started laying eggs, they were moved to an aviary, multi-tiered aviary housing system at about 17 weeks of age. So when we look at the morphological parameters such as surface area and volume, just to orient you, A and B lines are the brown lines, and C and D are the white egg type chickens. So you can see that the brown birds tend to have slightly larger kill volume compared to the white lines. And then they also tend to have a greater surface area in terms of compared to the white lines in terms of the keel bone. And we all know there is differences in body weight between browns and the whites. So that may have contributed them to having slightly larger keel versus slightly smaller keel. But the important thing when we look at the fracture prevalence, there was line differences. So line A had the smallest or the lowest keel fracture prevalence, which was still around 80%, whereas the other lines had even higher keel fractures into the 90s. But those surface area or the volume measurements that we did, again, did not really correlated with the fracture prevalence. So you can probably sense a theme here, like a slight increase in density or a slightly bigger bone has not really impacted the keel fracture prevalence. So either the improvement are not sufficient or there is something else that is going on in these bones, right? So to summarize some of the work that have been done in terms of genetics or genetic differences between the birds, you can see that the line differences do exist. Some birds tend to have slightly lower keel fracture prevalence compared to the other birds. And then the breeding companies, so there was a nice little study that was conducted recently by Lohmann. I think Hendricks is conducting similar studies, same thing with Highline. And they have started looking at some of their pure lines and crossbred lines to see if there is some genetic variability and if they can be used for selection against keel fractures. So what we have seen is what people have reported is there is anywhere between 15 to 30% heritability for keel fractures. So which is a promising sign that essentially tells you maybe up to 40% of the variation is explained by genetics, and there is a chance of genetic selection against these birds. However, parameters such as cell strength, egg weight, body weight did not correlate with the keel fracture prevalence in terms of genetic correlation. So there was a long-going debate, still an ongoing debate about if these birds are starting to get a lot of fractures because we have selected them for larger amount of egg production or producing eggs for a longer cycle. So there might be some physiological repercussions, but at the genetics level, there was no association. However, there was an inverse relationship between the keel status or the keel damage status and the onset of egg lay. Birds that tend to come into egg lay earlier were having more keel fractures compared to the birds that were coming into layer slightly later in the production. So, but that was again on the genetic correlation side. So we wanted to test that, and I'm not presenting the results here, but we tried to use lights and restrict the light during the growing phase to see if we can delay the onset of egg lay. And these modern commercial birds, it's very difficult to make them not to lay eggs when they reach certain age. By keeping just light hours at 8 hours a day until 20 weeks, we're only able to push back their egg production by about 10 days. And that did not make any difference in the keel bone parameters. So we used some 1940s leghorn from University of Arkansas, and we had a commercial strain to compare it with. The 1940s leghorn did have some positive skeletal parameters when you delayed their egg laying further. They were already coming in at 21 weeks compared to 18 weeks with highline, but when you delayed them, there were some positive skeletal changes, but not in the commercial lines. Or we did not see any difference in the keel fracture status early on. So what about when the fractures start to appear in these birds, and if it keeps increasing, or what happens with the stage of production? So these lines in this graph, the blue lines are aviaries, the gray line is the enriched colony cases, and then the yellow or the orange lines are the conventional cases. Regardless of how you rear these birds, you can see that until 18 weeks or until when they were moved into the hen house, there was no fractures. We looked at birds that were a large number of samples, and you could see maybe one or two, a few birds that had fracture, but not to the extent that we were hoping. So there is no fractures until 18 weeks or until the end of pullet phase. But by the time they reach 26 weeks, there is already about 30% fractures. And by the time they reach 56 weeks, there is already about high 70s, fracture prevalence in the high 70s. And then after 56 weeks, the fracture prevalence start to plateau. Maybe most of the birds have already fractured their bones by then. Maybe the keel is finally completely mature by then. So there are some things there, but this was our result, but the same results have been consistently produced by other groups in Europe as well. So after 56 weeks, you start that fracture rate, incidence start to go down a little. So it was intriguing for us to see why there was no fracture until the birds were 18 weeks of age. Was it like, so initial thoughts were, oh, maybe now they're starting to deposit more calcium into the egg cell, what is going on? So we decided to look at it a little bit in a close detail. First, before we go into a lot of those, I just wanted to explain to you that keel is a very unique bone whenever which makes it really challenging and also interesting, because so when we look at bone strength and the data that I showed you earlier about tibia and humerus, it's easy to, or much easier to measure those mechanical properties of those bones because they are a cylinder. You can break them by 3-point bending, 4-point bending, many different methods. But keel is a prismatic, more or less triangular kind of bone with a very less uniform shape. And then those conventional method of measuring the fracture resistance and bending strength does not apply to them. So there is not really a proper way to test the mechanical properties of these bones. And then when we look, so they are very different in their anatomy. And then when we look at their ossification and growth, so the long bones in chicken's body, they pretty much completely ossify by the time they're about 12 weeks or so. But keel bone, so you can see they have a large cartilaginous portion while they're growing. And when we look at the keel bones, by the time they were about to move to the hen house at about 17 weeks, or in terms of sexual maturity, by the time they're about to start producing eggs, there was still about 10% of their bone length uncalcified or completely cartilaginous. So there is this school of thought that once the bird starts to lay egg, any calcium that they get from the diet goes towards forming medullary bone or goes towards egg cell calcification and does not really contribute to the structural property of the bone. So is it that since the bone grows a little bit slower, is it that these birds enter into the lay cycle and that further slows down the growth of this keel bone or the ossification of this keel bone? And is that the reason that you start to see some fractures when because of this growth of the keel bone itself? So, and then when we look at the fracture location, because if the bird bone is weaker towards that caudal tip where it was still cartilaginous, then you would expect to see most of the fractures there, and which was actually the case. So a lot of fractures were seen in the caudal area of the bone. And then remember, like when I said, if you just look at in terms of yes or no for fractures, you will almost see no difference between a case and a case-free. But when you look at the location of the fracture, you see that the orange bar, which is the conventional case, you see most of the fractures were only localized to the tip of the keel bone. And then there would be very minor fractures, sort of like a slippage of the growth plate, or these green stick fractures you would see in children with younger bones or immature bones. So that essentially means that even though the fracture happens in cases, the birds don't have more extensive movement, so the fracture heals quickly and you only see a minor scarring or a damage there. Whereas in the case-free houses, the birds fracture their bone, but they're still moving and jumping around, so the bone never really gets enough time to heal properly. So you start seeing large deposition of this fractured callus material or severely deformed keel bones. But regardless of the housing type, still majority of fractures were located towards this caudal 1/3 of the bone. So again, trying to delve a little bit deeper into what happens during that 18-week, why don't we see the fractures there and why we start to see a sudden rise in fractures? We started to look at what happens during the rearing to lay transition, and what Elizabeth was trying to explain earlier, these birds go through change of housing system at that point. In US laying hen system, pullets are grown in a separate facility, and then the hens are kept, once they are ready to lay eggs, then they are moved into a separate facility. Depending on where your grower contractors are, this could be anywhere between 50 miles to 100-mile radius from the pullet house to the hen house. So at that time, the pullets had to go undergo a catching exercise. They are loaded into the trucks and then moved into the hen house. The hen house is a completely new environment for them because now it has a nest box. They have to learn to use that nest box to lay the eggs. They have to learn to use or navigate that three-dimensional space of the aviaries properly. So that causes a significant stress on them. And then there are studies that has reported that this catching, handling, transportation stress could cause some immune changes and could cause some dysbiosis of the gut. So we wanted to look at if that was something that was going on in these birds. So we did an experiment where similar housing system like I showed you before. So the pullets were reared in a floor and a slat system. And at the time they were about to lay eggs, half of them were moved to the aviary house. So we caught them, drove them around for about 20 minutes and moved them into the house. And then half of the pullets were just left into the same house. And then we just fitted nest box into them for them to lay eggs. Then, so from here on, I will refer to the birds that were moved to the aviary system at 17 weeks as AC group, and then the birds that were just left on the floor as FC. So what we did was we look at some inflammatory markers and anti-inflammatory cytokines, some of the conventional gene expression assays on those samples. We looked at the bone samples. We did the breaking strength of the tibia and humerus, and then we looked at the keel bones, and we looked at radiographic densities and mineral content. And we also look at the microbiota, cecal microbiota profile through V4 and V5 regions of 16S RNA. And so just to highlight some of the changes, so this is the differentially abundant taxa between the floor and the birds that were moved to the aviaries. The green lines are the ones that the birds were kept in the floor, and then the red are the ones that were moved into the aviary. So this was 1 week after we moved them into the new house. And you can see that the birds that are moved to the aviary house had enrichment of Proteobacteria group or the Enterobacteriaceae group, which also contains most of the pathogenic bacteria that affects chicken. And then, interestingly enough, we also see a significant enrichment of this one group of bacteria, Thericibacter. And then at that point, when we were looking at that, there was not much study done in Thericibacter. There were some studies in humans where it had been associated with serotonin metabolism in the peripheral, serotonin metabolism in the gut. But now this bacteria has been isolated from turkeys and chickens, and it has been one of the major component of the bacteria that colonizes the gut during the growth or the initial colonization. So even that short catching, handling exercise and moving them into the hen house could make some changes into the bacterial profile. And that changes existed throughout until 24 weeks when we terminated that study. And then you could see, like on a broad level, those birds that were kept just continued to be kept in the floor system. They had Eukaryota and Bacteroidetes followed by Firmicutes as a dominant phyla, whereas in the birds that were moved, you could see it was characterized by enrichment of Enterobacteriaceae and Thericibacteriaceae. So based on the isolation of Thericibacter and what we had seen on the human side, so we decided to look at some of the serotonin receptors expression in the gut. And we saw that in the FC group here, they had a higher expression of 5-hydroxytryptamine 2B receptors compared to the AC group. And those receptors, there are literature to suggest that they're involved in differentiation of osteoblast, and they are recruited, or they can recruit osteoblasts to deposit more bones. So, and when we look at the, let's see if it comes. So when we look at the results of some inflammatory cytokines, so we looked at IL-1 beta and then IL-10. So IL-1 beta is a general pro-inflammatory cytokine which has been known to impact bone quality. So it is involved in osteoclastogenesis and differentiation of osteoclast. And then we saw that 1 week after we moved them to the hen house, the birds that were in the AC group or the birds that were moved had a higher or their increased expression of those inflammatory cytokines, but that was short-lived. The situation didn't change after that, first 18 weeks. And then corresponding to that rise in the IL-1 beta, you see IL-10 going up as well. So it sort of acts as a feedback to that IL-1 beta. And then when we look at the bone content, so after that initial dysbiotic changes and inflammatory changes, you start to see some effects on the bone at 22 weeks in the bone mineral content and the bone density. So you can see birds in the aviary control group or the birds that were moved to the aviary house start to lose some of those bone mass there. And that was reflected in the breaking force as well. Here, there is that I want to express slight caution though, that it was not just that catching, handling, and transportation exercise that we did, right? So we moved them to a completely new housing environment. So, and bone is very dynamic. So even if you stop moving, so if you are a bird that was moving constantly or running around, and then you suddenly stop doing that for a week, you can have a significant loss of the bone. So I do not have data to say like when we moved them into the new house where the birds were still physically active as they were on the floor or not, and that could have affected some of those studies, but you could also sense that some of these dysbiotic or inflammatory change could also be correlated to the bone strength in these birds. So to summarize the results, significant differences in gut microbiota during the pullet hen transition, and then you can that was corresponding with some inflammatory changes as well. Although we do not know if that was just a correlation at this point or if there is a cause and effect relationship, and there needs to be further studies related to them. But looking at the keel bone fracture again, so there were other risk factors that have been associated with it, like perch design, if it's a metal perch, if it's a round or a circular perch or a rectangular perch, that has been known to impact the fracture prevalence. Some study that was done in Germany has reported that the plastic perch that was lined with foamy materials was able to reduce the keel fracture by certain percentages. Same thing is as the placement of perches. If you remember back on one of the slides where I showed that single tier aviaries had the most prevalent keel fracture, that was probably because it was the single tier, but then the perches were placed, aerial perches were placed all over the house. And then when a bird dropped, it was a more steep and a significant drop from those heights and more likely to fracture the birds. Flooring material has also been associated with it. And then space between the two rows of aviaries has been associated with it. And that dictates if a bird is able to make a clean jump from one row to the another row, or if they cannot make it, if it is spaced out a bit too far. So there are these other factors that people have looked at. And some group have installed ramps and then changed the perch material. So I didn't really go into the management of these fractures yet, because I think like we still need to understand a little bit more about how these fractures are happening. So, but nutritional management, these husbandry changes, housing design, all of these have been able to reduce the keel fractures by about 20 to 30%. So if you look at the prevalence of fracture, that means we're only reducing from 90 to 60 or 80 to 50%. So there is still a large number of birds that are going through these fractures. And then the last bit of experiment or the results that I want to show you before we can all go out for lunch is, so we saw that there is a clear difference between the bones of birds that were kept in cages versus cage-free, right? But how about how the birds that were using the system? Because we have seen, like I told you, there were birds that had 80% keel fractures, like flock that had 80% of their hens with keel fractures. But that also means like there were 20% of the birds that went through that 80 weeks of production without incurring any keel fractures. So we started trying to look at if there is a relation between how the hens were using that system, aviary system, and if there is any relation to the fractures. So to do that, what we did was we used some RFID tags to track the birds and track their movement in the aviary houses. So this is a representation, this is the housing system that we used, and the yellow dots represent where we had the RFID antennas. So that means we had the RFID antennas at the entrance of each level, so the bottom, middle, and the top. And in this housing system, the nest boxes were on the top tier. So when we look at the data, it was quite interesting. So like with people, I guess, in chickens, there are some very active chickens. And then there are some like me who don't like to run around or do much. And so when you look at the graph there, so that's hen 7 and hen 8, just random numbers of the hens, but that's their consecutive daily movement for during the light hours. So you can see that on 2021, 5/7, 5/8, 5/9, so consecutive days, right? So it looks very consistent for that particular bird throughout the day. And then that bird keeps moving between top, middle, bottom, top, middle all day, and moves a lot. Whereas the other bird number 8, you can see that it has one bout of movement to the top tier in the morning. That's probably because the nest box was there and it had to go up there to lay the egg. But other than that, didn't move much at all. And it spent days on the bottom tier, not moving much. So what we did was depending on the frequency of the transition between these different tiers, so we tried to divide or categorize these birds into low activity, medium activity, and high activity birds. So, and it sort of came to like 1:2:1 ratio. So we had about 33% of the birds that were very low active, and then about 43% birds that were medium activity, and then about another 23% that was very high activity. So we calculated or categorized them based on if the birds made less than 4 movements or 4 transitions between different tiers, they would be low activity. Anywhere from 4 to 12 would be a medium activity birds, and a bird that moves around more than 12 transitions per day in those tiers, that would be a high activity bird. So, okay, so what does it mean, right? So we have some really low active birds and some really high active birds. And based on all the data that I've showed you previously, remember that I told you the birds were moving, their bones were getting bigger, and then the bones were stronger. So we decided to look at their bones. So the keel fractures and deviations. So Score 0, no fractures. Score 1, a single fracture and not much deformation. And score 2, multiple fractures with large deviations, right? So you could see that the lower activity birds either had some minor tip fractures or no fractures at all. But if you look at the high activity birds, even without missing, those birds had very severe keel fractures with multiple fractures in those bones, right? And then, so I didn't show you the data from the tibia, but when I looked at the tibia volume and density and mineral content, it was the opposite. Those birds that were not moving much, they had less volume, which is understandable, but they also had denser tibia compared to the birds that were moving quite a lot. So now all my PhD work was sort of thrown into bin, but then this time around, I was comparing, so all these birds were from the same flock, they were kept in the same housing system, right? So this is within flock differences, whereas the other studies were between housing types, right? So now we're trying to delve a little bit deeper into the question, right? Are those birds that were always staying in the bottom, are those the ones that are also lower down the pecking order in the social ranking or hierarchy? And are these the birds that are the ones that are infrequent egg layers? So no matter how much exercise you do as a chicken, if you don't lay eggs, then you might have a better chance of having more minerals in your tibia. So are these birds having more dense tibia because they are not laying eggs in a regular manner? Because we know, like, even in a really good production in stage at about like 30 weeks, you only reach as high as 94, 95%. So it'll be interesting to look more into that data. So to summarize all the studies so far, what we know about keel bones and what we know about bones in these systems. So by moving from cage to cages, we brought about some positive changes in the skeleton of the chickens, but this keel fracture problem still remains. And that is all, most of those fractures are more extensive, and that is a negative thing that is going on. So like with any other welfare issues, keel bone fractures also seems to be a multidimensional or multifactorial issue with implications from housing, genetics, nutrition, husbandry management, all of those factors. And some of those other confounding factors could be the stresses that we subject them to, and then how the birds are using the system structures within the housing system. So once we start moving into managing these keel fractures, it has to be a combination of genetic selection with favorable housing design and nutrition. So with that, I had some really good collaborators. So Darren from Michigan State, now at Purdue, he was my PhD advisor, and we still collaborate on projects. Kara, who helped with CT analysis, and Eves and Nolan were my grad students who did gene expression work. And Dr. Kwan and his grad student here were the one who helped us with the microbiome analysis. And we're funded, some of our projects were funded with FR and US Poultry and Egg. And thank you. And I would like to take any questions that you might have.
Questions for our speaker? You only went slightly over.
Oh, really? So he's over. Oh.
So I'm curious on your on all the flocks that you were comparing on their, if you use the same ration.
Yes, more or less. So depending on which genetic lines we used, we pretty much use the breeder's guideline.
So did you do any supplementation with vitamin D or calcium or any other?
So yes, so I didn't show the results of the study because I was not really trying to discuss the management side of keel fractures, but we recently completed a study where we had supplemented the bird's diet with vitamin D. It was a high DA product from DSM, I think, 125 dihydroxy vitamin D3, and then we also used fish oil and flaxseed oil. Vitamin D and fish oil brought about some positive changes. again, there was some increase in density. The bones were slightly larger, but the keel fracture prevalence, again, didn't change much between the groups. So we tried to maintain the ratio of N3 to N6 at a 4:1 in our diet. And for the vitamin D, I think the supplemented groups, the basal group had 2760 IU, and then the supplemented group had 5,500 IU of those high D product incorporated. So fish oil group was the one that was the most promising, and it was able to reduce the keel fracture score. So on that study, we started doing the longitudinal CT scan. So we were able to follow the same bird at multiple time points without euthanasia. And then when we look at the fracture score based on that, fish oil was the one that decreased the fracture by about 18%. Again, that essentially meant like we went from about 85% to about 70% in those groups, whereas everybody was quite high in terms of fracture. Yep. Looks like everybody's anxious for lunch.
So we have one question from a virtual attendee, or two questions now have just come through. Is the keel damage related to any myopathy symptom of breast muscle? Does the damage in the bone cause calcium ion leaking and cause abnormal muscle contraction, then lead to myopathy?
So not to the extent that I know in terms of molecular changes that occurs around the muscles, but so it is very interesting because we do not see very many inflammatory changes around the bone fractures, even when so if you catch the bird when the fracture had just occurred, you can see some hematoma and some swelling around those breast muscles. But these birds in a flock, unless you go and catch a bird and palpate, you're not going to notice if the fracture happened yesterday or the fracture happened 3 weeks ago, right? Or many months ago. So, but I have seen some swelling and some inflammation and some hematoma around the keel fractures if I happen to catch them when the fractures was fresh. There was a group from Denmark, I think they published a paper in 2020 where they were trying to characterize the histological or histopathological changes during the fracture. And it was very interesting that they did not see any inflammatory changes, even in the old healed fractures or fresh fractures. There was no recruitment of lymphocytes around those fracture area. There was no fibrous tissue scarring in those areas. So they sort of hypothesized that most of the fractures that they observed in the study was not of a traumatic origin because it lacks some of those inflammatory markers. But I tend to believe like there is both a mixture. So there in cage-free, there are birds that get traumatic fractures, but like I showed in cages where there is those minor trip fractures where it doesn't change much, there is no fracture callus material, then in those you probably lack any other associated changes that you traditionally associate with a fracture of other bones.
Any other questions from the audience? It's about ready, so we've got time for one more question. All right, we have one online here. You want to ask it?
The question is from Ruth Newberry. Do you agree with the interpretation that laying large eggs at an early age can cause keel tip breakage? And have you any comments on the impact of early life experience of a 3D environment, ramps, tiers, etc.?
Yeah, so to the first question, so at this point, we only know of genetic correlations between those early coming into early production and then keel fracture status, which shows that if a bird is coming early into production, that makes them more vulnerable to keel fractures or more correlated with keel fractures. But like I said, the experimental level study to create a scenario where you have a bird or a group of bird that is coming into lay early and then a group of bird that is coming into lay. We did that exercise by using light restriction. But like I said, these modern birds, if they don't get the cue from lighting, they'll get the cue from their fat pad or body weight. And then it has to be a combination of restricting their body weight and using lower light to maybe delay the onset of egg lay by about 3 weeks. So there is not really any experimental studies to prove that claim of genetic correlation, but there might be. And then the second question, what was the second question?
Asking about the commenting on the experience, early experience of a 3D environment.
Yeah, so Meyer and Richard's group in UC Davis and Tina Widowski's group in Guelph has done bunch of work related to how exposing the birds to those aviary environment early in their life, giving them access to that vertical spaces, help them navigate the environment better when they go into lay cycle. And they have seen some, so Tina's group has again seen some positive changes in bone parameters and lower down the keel fractures when the birds were exposed to the similar rearing environment compared to the laying environment. But some of those studies, I think they're still publishing, especially with the UC Davis group, they're still publishing those results. So I'm waiting for those to be published to read.
Me too. Thank you very much.
Thanks.
All right, we will now go to lunch and come back promptly in about 45 minutes. And if you have requested a special meal, there are some folks out there that you can talk to that will get it for you. And yes, thank you. We shall take a break now.